Hello and welcome to our astronomy course. Today we are going to study a galaxy. When a supernova explodes, the core collapses to a very small size. And theory predicts that the collapsing core cannot support itself as a byte or if its mass is greater than 1.4 solar masses, so-called the Chandrasekhar limit. Okay? If its mass lies between 1.4 solar masses and about 3 solar masses, it can halt its contraction and form a neutron star. A neutron star is supported by the pressure of the degenerate neutron. Theory predicts that a neutron star should be about 10 kilometers in radius, so tiny in the space value, right? And spin very, very fast because it conserves angular momentum as it contracts and have a powerful magnetic field. Stars, rapidly pulsing radio sources, were discovered in 1967. The Lighthouse model explains pulsars as spinning neutron stars that emit beams of radiation from their magnetic poles. As they spin, they sweep the beams around the sky like lighthouses. If the beams sweep over the Earth, astronomers detect pulses. The short pulses and the discovery of a pulsar in the supernova remnant called the Crab Nebula were key evidence that pulsars are neutron stars. A spinning neutron star, slow as it radiates its energy into space. Most of the energy emitted by a pulsar is carried away as a pulsar speed. And theory predicts that a neutron star cannot have a mass greater than about 3 solar masses. Dozens of pulsars have been found in binary systems, and those objects allow astronomers to estimate the masses of the neutron stars. Such masses are consistent with the predicted masses of neutron stars. Observations of the first binary containing 2 neutron stars reveal that the system is losing orbital energy by emitting gravitational radiation. In some binary systems, mass flows into a hot accretion disk around the neutron star and causes the emission of X-rays. X-ray busters are systems in which matter accumulates on the surface of the neutron star and explodes. The fastest stars, the millisecond pulsars, appear to be old pulsars that have been spun up to high speed by mass flowing from binary companions. Planets have been found orbiting at least one neutron star. It's for that. They may be the remains of a companion star that was mostly devoured by the neutron star. If the collapsing core of a supernova has a mass greater than 3 solar masses, then it must contract to a very small size, perhaps to a singularity, an object of approximately 0 radius. Near such an object, gravity is so strong that not even light can escape, and the region is called a black hole. The outer boundary of a black hole is the event horizon. No event inside is detected. The radius of the event horizon is a Schwarzschild radius, amounting to only a few kilometers for a black hole of stellar mass. If you were to leap into a black hole, your friend who stayed behind would see two relativistic effects. They would see your clock slow relative to their own clock because of time dilation. Also, they would see your light redshifted to longer wavelengths because of the gravitational redshift. You would not notice this effect, but you would feel powerful tidal forces that would deform and heat your mass until you grew hot enough to emit X-rays. Any X-rays you emitted before reaching the event horizon would escape. To search for black holes, astronomers must look for binary star systems in which mass flows into a compact object and emits X-rays. If the mass of the compact object is greater than about 3 solar masses, then the object is presumably a black hole. A number of such objects have been located. Black hole and neutron stars at the center of accretion disk can eject powerful beams of radiation and current. Such beams have been detected. Gamma ray bursts appears to be related to violent events involving neutron stars and black holes. Bursts longer than 2 seconds appear to arise during hypernova, the collapse of massive stars to form black holes. The short gamma ray bursts are produced by shifts in the powerful magnetic fields in magnetars or the merger of binary compact objects such as neutron star pairs or neutron star or black hole pairs. And now let's start new topics today's lecture. It's a Milky Way galaxy. The stars you are used in the title of a popular astronomy book written by James S. Pickering in 1948. You would have liked that book back in 1948. Also, it has gotten a bit out of date over the last 8 decades. The point of its title is that the stars belong to everyone equal, and you can enjoy the wonder of the night sky as if you open the stars may indeed be yours. You live inside a galaxy, one of the large star systems that fill the universe. Our Milky Way galaxy contains over 100 billion stars. If Earth is the only inhabited planet in the galaxy, then the galaxy belongs to all of us. Okay? Share it equally. Each person on Earth owns 15 stars plus any associated planets, moons, comets, and so on. Even if Earth must share the galaxy with a few other inhabited planets, you are rich beyond any dream. You lack only the transportation to visit your dominion. As you read and listen in our lecture, You will learn about our home galaxy, but you will also learn how the stars in the Milky Way galaxy have, generation after generation, made the atoms in your body. As you begin, as you begin our lecture, it may seem that the stars belong to you, but by the end of this lecture, you may decide that you belong to the stars too. You know, it seems odd to say that astronomers discovered something that is all around us, but it isn't obvious that we live in a galaxy. We are inside, and we see nearby stars scattered all over the sky, while the more distant clouds of stars in our galaxy make a faint band of light cycling the sky, as you can look on a figure A on the left part of this. The ancient Greeks named the band galaxies Kuklos, the Milky Circle. The Romans changed the name to Via Lactea, Milky Road, or Milky Way. It was not until earlier in the 20th century that astronomers understood that we are inside a great wheel of stars and that the universe is filled with other such star systems. Drawing on the Greek word for meal, they call them galaxies. Almost every celestial object visible to your naked eye is part of the Milky Way galaxy. The only exception visible from Earth's northern hemisphere is the Andromeda galaxy, cataloged as M31, just visible to your unnaked eye as a faint patch of the light in the constellation Andromeda. Seen from a distance, our galaxy probably looks much like the Andromeda galaxy, as you can see on the right part of this slide, more lower bottom part. Okay? Galileo telescope revealed that the glowing Milky Way is made up of stars. And later, astronomers realized that the sun must be located in a great wheel-shaped cloud of stars, which they called the star system. Only a wheel-shaped cloud produced the band of the Milky Way encircling the sky. In 1750, Thomas Wright, drawing on the technology of the time, referred to the wheel-shaped star system as a greenstone universe, by analogy with the thick disk of the stone used in milk. The English astronomer Sir William Herschel and his sister Caroline Herschel, also a talented astronomer, attempted to gauge the true shape of the star system by counting stars in 683 different directions in the sky. Where they saw more stars, they assumed the star system extending farther into space. They plotted their result to create a diagram showing an irregular disc shape with the sun located near the center. That confirmed the greenstone model of the universe. In some direction in the sky, the Herschel saw very few stars, and these holes in the sky produced great irregularities along the edge of their diagram, as shown in this plot. Modern astronomers know that these empty spots are caused by dense clouds of gas and dust inside the Milky Way galaxy that block the view of more distant star. But the Herschel, like many early astronomers, did not understand the importance of gas and dust in space. Also, they thought they were seeing to the edge of the star system. They were actually seeing only as far into the Milky Way as the gas and dust permitted. Because, because they counted similar number of stars all around the Milky Way. And they concluded that the sun was near the center of the greenstone universe. The model proposed by the Herschel was widely accepted and studied by other astronomers. The Herschels were not able to measure the size of the star system, but later astronomers were able to estimate distances to stars in statistical ways, and they concluded that the star system the Herschel had mapped was only about 15,000 light years in diameter. As the 20th century began, astronomers believed that the sun was located near the center of a rather small wheel-shaped star system. How the human race realized the truth about their location in the universe is an adventure that begins with a woman studying stars, that pulsates and leads to a man studying star flight. It is a common misconception that of poets that the stars are eternal and unchanging. Astronomers have known for centuries that some stars change in brightness. You already know that novae and supernovae appear, grow brighter, and then fade, but many other stars change periodically, growing brighter, then fainter, and then brighter again. Some of these visible stars are eclipsing binary, but some are single stars that pulsate like beating hearts. In 1912, Henrietta Leavitt was studying a star cloud in the southern sky, known as the Small Magellanic Cloud. On her photographic plate, she found many variable stars, and she noted that the brightest had the longest period, the time it takes a star to complete a cycle from bright to faint to bright. She didn't know the distance to the cloud, so she couldn't calculate the absolute magnitudes of the stars. But because all of the variables were at nearly the same distance, she concluded that there was a relationship between period and luminosity. The stars Leavitt saw, Cepheid variable star, are named after the first such star discovered by Delta Cephei. Many Cepheid variables are known today. They have periods from 1 to 60 days and lie in a region of HR diagram known as the instability string. Okay, you might found this one. From their position in the diagram, you can tell that Cepheid are giant and supergiant stars. A related kind of variable star, an RR Lyrae variable star, named after the variable star RR in the constellation of Lyra, and has a period of about half a day and lies at the bottom of the instability strip. Stars in the instability strip are unstable and pulsate because a layer of partially ionized helium is in just the right place in the star's atmosphere. to absorb and release energy like a spring. In hotter stars, the layer is too high to make the stars unstable, and in cooler stars, the layer is too low. Stars in the instability strip happen to have this layer in just the right place to make them pulsate as energy flows out of their interior. As stars evolve into the instability strip, they become unstable and pulsate. When they evolve out of the strip, they stop pulsating. Massive stars are very luminous, and they cross the instability strip higher in the HR diagram. Because these massive stars are larger and they pulsate more slowly, just as large bells vibrate more slowly and have deeper tones. You will remember from an earlier lecture that favorite star Polaris is a supergiant. It lies high in the instability strip and pulsates as a Cepheid variable. Lower mass stars are less luminous, cross the instability strip lower in the HR diagram. And because they are smaller, pulsate faster. This explains why the long period Cepheids are more luminous than the short period Cepheids. Levy first noticed this in 1912, and it is now known as the period luminosity relation. The physics of pulsating stars was unknown in 1912. But when Leavitt noticed that the Cepheid period of pulsation was related to its luminosity, she found the key that unlocked the secret of the Milky Way. Earlier, in the 20th century, when Henrietta Leavitt was studying the photographic plates, astronomers believed that they lived near the center of disc-shaped cloud of stars that they called the star system. Many believed that the star system was isolated in an otherwise empty universe. A young astronomer named Harold Shapley began the discovery of the true nature of the Milky Way when he thought about different kinds of star clusters. In an earlier lecture, you met open clusters and globular clusters. Open clusters are concentrated along the Milky Way, but globular clusters are widely scattered. Shapley noticed that the globular clusters were more common toward the constellation Sagittarius and Scorpio. Shapley assumed that this great cloud of globular clusters was controlled by the combined gravitational field of the entire star system. In that case, he realized he could study the size and extent of the star system by studying the globular cluster. To do that, he needed to measure the distances to as many globular clusters as possible. Globular clusters are much too far away to have measurable parallels, but they do contain variable stars. And Shapley knew of Henrietta Leavitt's work on these stars, and he knew that she had been unable to find their absolute magnitude. He also knew that knowing the absolute magnitude would tell him the distances to the star cluster. So he tuned his attention to variable stars. All stars move through space. I hope you remember this. And over periods of a few years, these motions, known as proper motions, can be detected as small shifts in the position of the stars in the sky. The more distant stars have undetectably small proper motion, but nearer stars have larger proper motion. And clearly, proper motions contain clues to distance, right? Also, no Cepheids were close enough to have measurable parallax. And Shipley searched catalogs of proper motion observations and found 11 Cepheids with measured proper motion. Through statistical processes, he was able to find their average distance, and from that, their average absolute magnitude. And that means he could replace Leavitt's apparent magnitude with absolute magnitudes on the period luminosity diagram, as shown in this diagram on the left part. That he knew how bright the variable stars really got. Finally, he was ready to find the distance to the globular cluster. He could identify the variable stars he found in the clusters, and he could measure their apparent magnitude from his photograph. Their short period of pulsation altered Shapley that the variables in his cluster were RR Lyra variables, and comparing their apparent and absolute magnitude gave him the distance to the star cluster. Note how sharply proceeded step by step in his research. Astronomers say he calibrated the variable stars for distance determination. Shapley later wrote that it was late at night when he plotted the direction and distance to the globular cluster, and found that, just as he had supposed, they formed a great swirl. But the swirl was not centered on the sun. The center lay many thousands of light years away in the direction of Sagittarius. The star system was much bigger than anyone had suspected. And he found the only other person in the building a cleaning lady. And the two stood looking at his graph as he explained that they were the only two people on Earth who understood that humanity lives not at the center of the small star system, but in the suburb of the vast wheel of stars they carry. It is interesting to know that Shapley made two mistakes. First, he assumed that space was empty. Later, astronomers realized that the interstellar medium dims the more distant stars and makes them look farther away than they really are. Also, Shapley didn't know that there are two types of Cepheids. Those he saw in his cluster were the fainter type, but those he used for calibration were bright. The meant he overestimated the luminosity of his cluster star and overestimated the distance to the cluster. Consequently, his estimate for the size of our galaxy shown on this figure and was bigger than the modern value. The point is not that he made a few errors of calibration, but that he got the main point right. We live not at the center of a small star system, but in the suburbs of a very big wheel of the star. And it is not surprising that astronomers at first thought that the star system was small. When you look toward the band of the Milky Way, you can see only the neighborhood near the sun. gas and dust make most of the star system invisible, and like a traveler in a fog, you seem to be at the center of a small region. Shapley was able to observe the globular clusters at greater distances because, because they lie outside the plane of the star system and are not dimmed very much by gas and dust. Building on Shapley's work, other astronomers began to suspect that some of the faint patches of the light visible through telescopes were other galaxies like our own. Shapley and astronomer Herbert Curtis met in 1920 in a famous debate known as the Shapley-Curtis debate. Curtis claimed the faint objects were other galaxies, and Shapley argued they were not other galaxies, but were spheres of gas and stars in our star system. It isn't clear who won the debate, but in 1923, Edwin Hubble photographed individual stars in the Andromeda galaxies, and next year, he, in 1924, identified Cepheid there. Really, the faint patches were other star systems like our own. Our galaxy, like many others, contains two primary components, a disk and sphere. And this figure shows the components and other features that you will discover as you analyze the structure of our galaxy. The disk component consists of all matter confined to the plane of the galaxy's rotation. That is, everything in the disk itself. And this includes stars, open star clusters, and nearly all of the galaxy's gas and dust. Because the disk contains lots of gas and dust, it is the site of the most of the star formation and is illuminated by brilliant blue massive stars. Consequently, the disk of the galaxy tends to be blue. The dimensions of the disk are uncertain for a numerous of reasons. Its thickness is uncertain because the disk does not have sharp boundary. Stars become less crowded as you move away from the plane. Also, the thickness depends on what kind of object you study. All stars lie within a narrow disk only about 300 light years thick. But sun-like stars are more widely spread. The diameter of the disk and the position of the sun are also difficult to determine. Gas and dust block the view in the plane of the galaxy, and so you cannot see the center or the edge. The best studies suggest the sun is about 8 kiloparsec from the center, where 1 kiloparsec is equal to 1,000 parsec. This seems to be about 2/3 of the way from the center of the Earth edge. So, the diameter of our galaxy appears to be about 25 kiloparsec, which is about 80,000 light years. This is the diameter of the luminous part of our galaxy. The part you would see from a distance, and you will learn later that strong evidence suggests that our galaxy is much larger than this, but that the outer parts are not luminous. One way to explore our galaxy is to use radio telescope to map the distribution of unionized hydrogen. Fortunately for astronomers, neutron hydrogen in space is capable of radiating photons with a wavelength of 21 centimeters. This happens because the spinning proton and electron act like tiny magnets as shown in this slide. Depending on whether or not the electron and proton are spinning in the same or opposite direction, the atom can be in one of two energy levels. One level has slightly higher energy than the other. If left undisturbed, an electron in the higher energy level will eventually flip its spin and draw to the lower energy level. But when that happens, the atom is left with a tiny amount of excess energy, which is radiated as a photon with a wavelength of 21 centimeters. And that means that cold hydrogen gas floating in space and naturally emits radio energy. And radio astronomers can map our entire galaxy at a wavelength of namely 21 centimeters, because these long wavelength photons are unaffected by the microscopic dust grains. They scatter photons of light. And thus, a radio telescope can see our entire galaxy while optical telescopes cannot. Observations made at other wavelengths can also see through the dust and gas. Infrared photons have wavelengths long enough to be unaffected by the dust. And thus, a map of the sky at long infrared wavelengths reveals the disk of our galaxy. And the most striking features of the disk component are the spiral arcs, long curves of bright stars, star cluster, gas, and top. Such spiral arcs are easily visible in other galaxies, and you will see later that our own galaxy has a spiral pattern. The second component of our galaxy is a spherical component, which includes all matter in our galaxy scattered in a roughly spherical distribution around the center. This includes a large halo and the nuclear bubble. The halo is a spherical cloud of thinly scattered stars and globular clusters. It contains only about 2% as many stars as the disk of the galaxy, and has very little gas and dust. Because of this, no new stars are forming in the halo. In fact, the vast majority of the detectable halo stars are all full giants. Detailed studies, however, suggest that most halo stars are lower main sequence stars and old white dwarfs that are much too dim to be easily detected. The colors of other galaxies are generally too faint to detect. The nuclear bubble is the dense cloud of stars that surrounds the center of our galaxy. It has a radius of about 2 kiloparsec and is slightly flat. It is hard to observe because the disk does. If the disk scatters radiation of visible wavelength, but observation at longer wavelengths can penetrate the dust. The bubble seems to contain little gas and dust, and there is thus little star formation. Most of the stars are all full stars like those in the halo. When you needed to find the masses of stars, you studied the orbital motions of pair of stars in binary physics. To find the mass of the galaxy, you must look at the orbital motions of the stars within the galaxy. Every star in the galaxy follows an orbit around the center of mass of the galaxy. Astronomers can figure out the orbit of stars by observing how they move. The Doppler effect reveals a star's radial velocity, which can be combined with the distance to a star and its proper motion to reveal the size and shape of the star's orbit. In the halo, each star and globular cluster follows its own randomly tipped elliptical orbit. These orbits carry the stars and clusters far out into the spherical halo, where they move slowly, but when they fall back into the inner part of the galaxy, their velocity increases. And motions in the halo are like the random motion of a swarm of bees. In the disk, the stars follow concentric, circular orbits, and those motions can reveal the mass of the galaxy. The Sun is a disk star and follows a nearly circular orbit around the galaxy that never carries it out of the disk. By observing the radial velocity of the other galaxies in various directions around the sky, astronomers can tell that the Sun is moving about 220 kilometers per second in the direction of signals, carrying Earth and the other planets of our solar system along beside. Because its orbit is a circle with a radius of 8 kiloparsecs. And can you divide the circumference of the orbit by the velocity and find that the Sun completes a single orbit is about 220 million years. If you think of the Sun and the center of mass of our galaxy as two objects orbiting each other, you can find the mass of the galaxy by dividing the separation in astronomical unit u by the period in years squared to find the mass in solar mass. This calculation tells you that the galaxy must have a mass of at least 100 billion solar masses. This estimate is uncertain for a number of reasons. First, astronomers don't know the radius of the Sun's orbit with great certainty. Second, astronomers estimate the radius as 8 kiloparsecs, but they could be wrong by 10% or more. And this radius gets skewed in the circulation, so it makes a big difference, right? And second, this estimate of the mass includes only the mass inside the Sun's orbit. Mass spread uniformly outside the Sun's orbit will not affect its orbital motion. And thus, 100 billion solar masses are a lower limit for the mass of the galaxy. But not one knows exactly how much mass lies outside the Sun's orbit. Another thing that makes this mass estimate uncertain, complex motion of rotation galaxy, the motion of the stars near the Sun shows that the disk does not rotate as a solid body. Each star follows its own orbit and stars at different distances from the center of different orbital periods. And this is called differential rotation. Differential rotation is different from the rotation of a solid body, a carousel, for instance. And this wooden horse side by side on a carousel will stay together as the carousel turns. But the three stars lined up in a galaxy will draw apart because they travel at different orbital velocities and have different orbital periods. A graph of the orbital velocity of stars at various orbital radii in the galaxy is called a rotation curve. If all of the mass in the galaxy were concentrated at its center, then orbital velocity would be high near the center and would decline as you moved out. And this kind of motion has been called Keplerian motion because it follows Kepler's third law. A good example is our own solar system, where nearly all of the mass is in the sun. Of course, the galaxy's mass is not all concentrated at its center. But if most of the mass were inside the orbit of the sun, then you would expect to see orbital velocities decline at greater distance. Many observations confirm, however, that velocities do not decline and may actually increase at greater distance. These observations show that these larger orbits are enclosing more mass. Also, it is difficult to determine a precise edge to the visible galaxy. It seems clear that the large amounts of matter are located beyond the traditional edge of the galaxy. The edge you would see if you journeyed into space and look back at our galaxy. The evidence is clear that extra mass lies in an extended halo, sometimes called a dark halo or galactic corona. It may extend it up to 10 times farther than the edge of the visible disk and could contain up to 2 trillion solar masses. Some small fraction of this mass is made up of low luminosity stars and white dwarfs, but most of the matter is not producing any light. Astronomers call it dark matter and conclude that it must be some as yet unknown form of matter. You will continue to learn about dark matter in the following 3 lectures. It is one of the fundamental problems of modern astronomy. Okay? So I hope it's enough for today. Any questions or propositions? You may write me directly to email you see in this or containing to the comments near the lecture. So for this moment, I hope you enjoyed this lecture, and I'm, as usually, looking forward to seeing you next time. Bye.